Hello and welcome back to today's lecture on correlation. In this lecture, we're going to discuss Chapter 8, correlation topics, starting out with relationships. So what we're looking at in relationships are primarily the strength of the relationship between our two variables, the x variable and the y variable, and the direction of the relationship. And just a reminder here that our variables must be interval level variables because we have to calculate a mean and standard deviation, or we have to calculate a mean at least to get the correlation. And you can only do calculations that involve adding, subtracting, multiplying, dividing the actual scores when you have an interval level variable. So to reiterate, the mean as a measure of central tendency is only applicable for interval level variables. You can get a mode for any type of variable. You can get a median for a mean, or excuse me, you can get a median for an ordinal or an interval variable, but you can only use the mean when you have an interval level variable. I just want to review this. It's a theme that's going to really follow us throughout this class, is remembering to check your variable's levels of measurement. Check your variable and its level of measurement. It's going to affect the tests you choose. And as we move along from this point on, you'll see we're going to start exploring a number of different statistical tests and procedures for different research designs and different variable levels of measurement to help us guide us to the appropriate statistical test. And on your next exams, all of the remaining exams, part of the exam will be choosing the right procedure for a given research scenario. So I'll give you some research scenarios. You'll need to choose the right procedure. It's pretty easy in our next section because we are just basically our next unit is correlation and regression, which are very similar, and then probability, which is very different from them. So that'll make it pretty easy on the next test. But on exam 3, and especially on the final, choosing the right procedure will be a big part of exams 3 and the final. So keep that in mind as I'm going along, that when I'm emphasizing these things, I'm building us consciously to a particular end point. That's really important if you want to actually be able to use these skills in a real life context. So the first thing when we're thinking about correlation is to remember that correlation just looks at relationships. Specifically, we tend to call it correlation is an association or correlation. Those terms are interchangeable, and it's in the category of relationships broadly speaking. These are not causal. We can't draw causal conclusions from this set of procedures. We can only draw conclusions about general relationships, and we'll have other tests that will fall into this relationship category, and then some tests that will allow us to draw causal conclusions or be applicable to observational data. We'll break this down a little more in our lecture on regression, and then again when we get to hypothesis testing. In correlation, the two main features of the relationship are the strength and the direction. The strength of the association is generally associated with the correlation coefficient itself. And if there's a strong association between two variables, then if you know one variable, your x variable, that helps a lot in predicting the other, as we discussed, the y variable. Now, why couldn't you know the y variable and predict the x? You certainly could, but we, by convention, make x predictors or independent variables, and they're associated with y, a single outcome. But in correlation, sometimes we can't identify a specific predictor and outcome. So if you are faced with a situation where it's unclear, that happens. It's to be expected. The other thing to remember about association is that if there's a weak association, a low correlation, then knowing the x variable doesn't help you in guessing the other one because they only have a small degree of correlation. We also look at the direction of the association. So this is very important to keep in mind because it maps directly onto how we will interpret correlation problems. And don't worry if you're concerned about, well, we just discussed how important it is to know what kind of test to do. Are we going to get lots of practice doing that? Absolutely. I'm going to be adding into our lectures more and more practice doing that, but we do need to know some of these tests before we can do much in the way of practicing choosing among them. So don't worry, more of these scenario-based examples are coming, but we need to know these basics in order to layer on the more complex skills. In terms of the direction of the association, a positive correlation means that as the cloud or the line goes up, one variable increases, the other increases. They go up together. In a negative correlation, they go as one variable increases, the other decreases. So we see them as in a positive correlation, they both go in the same direction. In a negative correlation, they're going in opposite directions. Now let's take a look at some scatter plots and get some practice just identifying what kinds of correlation are we looking at, what does different strengths and directions look like. So here we have several general types of correlation. We talk about correlation in terms of degree. If there's no correlation, the scatter diagram will be very dispersed like this. And as the correlation gets higher and higher, you see the lines clustering more closely to the line. When we have these four basic types of correlation here. We'll discuss, I think, one or two others, but primarily we'll look at positive correlations and negative correlations. These would be directions. We also have a curved type of correlation. This is sometimes called curvilinear. You can see how it generally follows a line, but the line is curved, and like when you reach this point in the middle here, the values on y start to go down. So the direction of the correlation changes at a point on the line, and that's a curvilinear. And it can also happen that you have a partial correlation where the variables are correlated to a certain point in the distribution. And if you've got these latter types, curved or partial correlation, then it's going to be, you need to use more sophisticated statistical procedures to deal with those situations. So for our purposes, you'll want to know that these types of associations exist, but we won't actually do math. We won't do the actual problems and procedures for dealing with these types of associations. If you find yourself in a scenario down the road where you need to manage, deal with a curvilinear association or a partial association, you can often find the procedures for dealing with these subtle changes in statistical procedure through a simple Google search. You'd be looking for a correlation procedures, curvilinear, and as you see we'll see on SPSS, there's a lot of options and different tests. So there's specific tests for dealing with these procedures. We won't learn those tests, in short, but you need to know they are out there and these things do exist. And now we have three possible graphs of y equals, and you can see here they're using the a plus bx terminology. This is from our OpenStax textbook, which I have recommended as your additional resource if you're looking for one. There's lots of problems in it, and there are and the answers are, I think, in the back of the book for everything. So it's really nice if you want some more clarification on a topic or more practice. Here we have three possible graphs of y equals a plus bx. Here for a, if b is greater than 0, if the slope is greater than 0, then the slope goes upward to the right. If it's 0, then it's flat. And if it's down negative, then it's going to slope downward to the right. This is a review from chapter 7. Let's just quickly go through and make sure we can see all of these different patterns discretely. So we've got a positive linear correlation. This is a strong association. We know it's strong because look how close these points are clustered to the line. This is a strong association, but we've got one outlier here, and that may or may not be important in a particular data set. It's only 1 point. We'd be more concerned if there were several outliers over there. You could have a negative pattern with a strong correlation. As x goes up, y goes down. And here we have a weak negative pattern, and we can see that it's weak because the points are distributed all around the line. And this is one other pattern we're going to look at, the exponential growth pattern. And you see this frequently in modeling of health processes sometimes and in social research. So I wanted to introduce it to you, although we won't deal with statistical treatments of exponential growth patterns. It's highly likely you could encounter this in reading or future work. And an exponential growth pattern shows an It shows an exponential increase in y for units of x. See that pretty discreetly by looking at these 2 points here. X goes up by a little bit, y goes up by exponentially more, a lot more. An exponent would be like squared. And when there's no pattern at all, you're going to see a plot where the points are all over the place. And here you can see the plotting the line and the beginnings of predicting the point on the line. So here you can see that when they're discussing prediction. So when x is x naught is how you refer to this x with a little 0, or y naught, my favorite one. And this little caret is for the predicted y. And so you can see that's just all they're telling us here. So we've got a point x, we want to predict y for point x. And so our line can tell us the association, but when we predict the points, they're not necessarily going to fall on the line. All the points for x will fall on the line, but our y prediction, our outcome prediction, is what we're really interested in. And I know that some of this is not in chapter 8, but I'm trying to, again, map us across the next couple chapters broadly because the exam is coming quickly. So I want you to start thinking about these topics now. And you see here, we've got just one more scatter plot identifying an outlier. And if you've got one, then an outlier, you need to just consider, based on your research design and the variables you're looking at, is this outlier separate from the population or for a good reason, or is this representing a real issue in the association between our variables? We're going to talk about populations and samples and comparing them a bit more down the road. So we'll deal with that theoretical question a bit later, but it's good to know generally how you'll deal with an outlier now. And I know it's an outlier because I can see on this graph the scatter plot. I can see the line plotted. And then these yellow bars tell us our margin of error around the line. And this outlier is outside of even our error term. The correlation coefficient, which we've been discussing a little bit up to this point, but we really want to get to know this well because correlation is very popular. It's a common scenario to have two interval variables. And when you have two interval variables, then the correlation is probably the most appropriate procedure. The correlation coefficient, that's R, is a measure of linear association clustering around the line. We saw that in the graphs we just looked at. And the relationship between the two variables can be summarized by taking the average of the x values by these 5 terms. We've got the average of the x and y variables and the standard deviation of the x and y values. And finally, the correlation coefficient, which we will use to give us an idea again about our strength and direction. And then you'll see we will also learn how to decide if the correlation is statistically significant. And this is going to be an important thing. So that statistical significance is going to tell us if that correlation is strong enough for us to draw valid conclusions based on the data observed. It's important to remember that correlations are always between -1 and 1, but they could be any value in between. And here we just see some general correlations plotted onto what should be by now really familiar graphs, so that if you saw any of these scatter plots, you would be able to identify that they were showing us a positive correlation, negative, or zero correlation, and to know that for A, for example, this is going to represent a correlation, a positive correlation. It's always going to be a value between that's above 0 and below 1. We almost never see a perfect correlation of 1 or -1. That doesn't exist generally in the real world. And again, we're excluding 0 too, because 0 is no correlation. You should also, from looking at a graph like this, be able to say this is a negative correlation, and to know that a possible value for the correlation seen in this graph could be from anywhere between -1 to just below 0. And finally, 0 correlation. Again, be able to know that this is going to always be a flat line, is always a correlation coefficient of 0. And here we see laid out some correlation coefficients of various strengths on scatter plots that have been produced in a standard statistical program. How do I know that? because they have a look. They have that look. Oh, excuse me. Here we see a zero correlation. There's no association at all. We couldn't possibly draw a line through here, except a flat line. With our correlation at 0.4, our lines are getting slightly more pattern within them, but 0.4 is still a pretty weak correlation. 0.6 is getting into a stronger range. And here we've got a 0.8 correlation. Oops. Excuse me. And my apologies that these bottom two are included. Those correlations are not included in our slides here, but they represent even closer clustering. So when a correlation coefficient is 0.9 or 0.95, which again you almost never see, then these points look quite clearly like a line. They're clustered very, very close together. And you can see that on page 127 and 129 of your book. Now let's do some of these problems. And I'd love it if you could try to participate here if you've got some ideas. Would the correlation between the age of a secondhand car and its price be positive or negative? Well, let's think about it. An age of a secondhand car. So as age goes up of a car, do we expect price to go down or up? Oh. Down, exactly. So what kind of correlation is this? Positive or negative? So car age is increasing, price is going to decrease. So now we can see clearly this is a negative. What about the correlation between weight and miles per gallon? Let's practice visualizing that. And how do I know which variable to put on which axis? Well, we would generally, convention would say weight would predict miles per gallon. And generally, as weight goes up, miles per gallon goes up too. Exactly. And just to, as an aside, point out a little bit of mathematical, or the intersection of mathematical and verbalizing the math. When you've got a slash here, that is a per, so miles per gallon, technically miles, divided by gallon, but you can read this as per or pretty much any variable. And this gives us a ratio here. We'll be dealing with more ratios as we go. So if you hear something referred to as a ratio or seen in a X per, one variable per another, that's just giving you a rate, and you could use that rate as your variable. As in this case, where it makes more sense to get our rate together, miles per gallon, than it would to look at miles or gallon. Those wouldn't be meaningful separately. Now, next we'll look at these scatter diagrams below and just think about the average of X and Y. Go ahead and think about A there. Oh. I guess you can't see, but if you could, it was pretty funny. I was trying to write on the book instead of on the tablet here with the tablet pen. So if the average of x is around for each scatter diagram below, the average of x is around which of these numbers? Well, let's take a look. We can see that there's a modest correlation here, probably about 0.4. That's not really important, but what we need to look at is our top values for x and our bottom value for x. So it ranges from 1 to about 5.5. And so the average for x, I would guess, to be approximately in the middle of these two, because we're assuming these are normally distributed. It's we would only use correlation if we had normally distributed x and y variables. So that's why it's fair to assume that these are normally distributed, which means the mean will be the score in the middle. And yes, thank you, Stephanie, it would be 2.5. Because these are outliers. Oops. Yeah, so our x average is going to be around 2.5. And the same for y, well, we can see that y has a much smaller range here. The bulk of the scores start at just under 1 to about just over 3. So where would we say that goes? Again, maybe nearest to 2.5. That's what I would say. Looks like it's about 2.5. You might be thinking, why would we need to? Well, it might be closer to 2. It's certainly not any of these, 3 to 4 or 1 to 1.5. Why would we need to eyeball so many things? Like the book asks you to eyeball things, because that's how you, when you're doing actual analyses, you check yourself. That's how if you're reading an article and you're thinking, boy, does this really make sense? Being able to just, look at this and get an estimation of where our different concepts or where different tests and calculations would fall out without doing calculations, without, just based on your knowledge of how the variables work. That's an important skill, and it's one that you'll find useful. The SD of x, or our standard deviation, is around, well, we can see our x variable ranges maybe around 2 to 4.5. So if 6 standard deviations fit within the range of a variable approximately, then we could say between 1 and, so the standard deviation is probably around 1 or 0.5. Honestly, I think it might be in the middle, because these outliers are going to make it increase a little bit. But this is why it's helpful to know that the standard deviation is equal to approximately 6 standard deviations fit within the range of a variable. And for y, the same quality is true. If y ranges from about 1/4 to about 3.25, then the range of y is about 3, so the standard deviation would be about 0.5. If this one's closer to 1, this one would be 0.5. When is this correlation positive, negative, or 0? What do we have on this first graph? This should be clearly a positive correlation to you. And we can see a negative correlation in our other graph. As x goes up, y goes down. And just looking at these, which one has a correlation closer to 0, regardless of the sign? Left or right? The first one, exactly. How do we know it's closer to 0? Because as the scores are more spread out, the correlation is closer and closer to 0. And just to hit home a couple points I mentioned as we were discussing the previous problems, the values for x and y as variables must be normally distributed in order for us to be even using the correlation as a procedure. And the y values for each x value are normally distributed about the line with the same standard deviation. And you can see that mapped out here on a plot on A and with a curved line on B. So what they're saying is that as you move further from x, as you move away from x, you can move down the normal distribution here of scores for the y variable. So we would know that the very large proportion of the y scores are going to be pretty close to the line. And as you get further, it's going to be increasingly unlikely to find y scores at all. And how am I getting to probability? It's just a little bit of review here. Remember that areas under the curve, under any normal distribution curve, correspond directly to probabilities. For each x value, the mean of the y values lies on the regression line. The regression line is the same line that we've been discussing. We just can call it the regression line. To ease into our terminology. And you can see the y values get further and further out. So you see this illustrated. I picked just a couple of questions from our next section to go over that I thought might be a little bit tricky. Investigators take a sample of dual income families, and they have data on the husband's income and the wife's income. So by definition, the family income is equal to husband plus wife. Average family income was around $85,000, and 10% of the couples had family incomes in the range of $80,000 to $90,000. The correlation between the wife's income and the family's income is, we should look here at these responses down below to choose. And more than one could be applicable here. Now, I guess not somewhat positive. I guess somewhat positive, we'll consider that to be maybe a correlation of about 0.5. So that's what I was thinking. So would we expect, let's first approach this as we did our early ones by thinking about the direction. Do we expect wife's income to be positively associated with the family income or negatively associated? Well, we're going to expect it to be positive, of course, because as the wife's income goes up, family income is going to go up. And so would we expect that correlation to be nearly 1 or 1, or just somewhat positive? 1, exactly. We would expect it to be 1 because the wife's income is part of this variable. Wait, sorry, let me back up a minute. We're just looking at the wife's income. So the correlation between the wife's income and the family income can't be a perfect correlation because, again, because there's 2, these are dual income families. So there might be cases where the wife's income is a larger proportion of the family income. And there might be cases where the husband's income is a larger proportion of the family income. And because of that, we can't have a perfect correlation here. Remember, there's almost never a perfect correlation. And so that's probably not going to be the answer for a lot of problems, or unless they are theoretical, which this one is theoretical, so that's a little tricky. So we know this must be somewhat positive because we can't control husband's income. Similarly, we would expect husband's income to be somewhat positively correlated with family income, again, depending on the size of wife income. B here, among couples whose family income is in the range of 80,000 to 90,000, the correlation between wife's income and husband's income. So now we're looking at a different aspect of the variable, looking at the correlation between husband and wife's income. Do you think that as husband's incomes go up, wife income? Well, let's break this down. If the family income is constant, so they're saying that the family income, we're only looking at couples in this range of 80 to 90,000, then the more the wife makes, the less the husband is going to make, and likewise. So they're likely to have a negative correlation that's somewhat negative to nearly -1, probably closer to nearly -1, because this is because we're just looking at this range here, just the specific part of the range. So we're holding total income constant within the 80 to 90 interval. If we were looking overall at the correlation between husband and wife incomes, then we could see that there's a somewhat weaker correlation. So it would be probably just somewhat negative if we looked across the whole data set. And let's look at this final item, true or false. If the correlation coefficient is 0.9, then 90% of the points are highly correlated. Do you think that's going to be true or false? Does correlation give us an exact percentage of the correlation of specific points? It's false. It doesn't. This is specifically important to remember that the correlation coefficient is not the same as a percentage. Unlike a proportion, which we can easily turn into a percentage, a correlation coefficient has some of the similar qualities mathematically in that it goes from, it has values between 0 and 1, or in the case of correlation, 0 and -1, but you cannot translate them into percentages. Correlation is accounting for the standard deviation in the variables, and it's giving us a summary statistic of their relationship. So it's not speaking to the correlation of individual points. Next up, we discuss the SD line. So this is another line that you see commonly on scatter plots when researchers have done regression. And this SD line goes through the point of averages, and it goes through all the points that are an equal number of SDs away from the average. So, and we'll take a look at some SD lines in just a moment. And the slope of the SD line is always going to be the standard deviation of y over the standard deviation of x. And this is a mirror to the slope formula generally, where we've got rise over run. So we still have rise here, the y variable, and run, the x variable, except we're looking at now the standard deviation of y. So we're going up by 1 standard deviation of y per standard deviation of x. So when we're plotting the SD line, we get the average, the standard deviation of x and y, and you can, as you see, they can be used just like the rise and the run. It doesn't matter if you're looking at a positive or negative correlation. And we're just about out of time here, so I planned this about perfect. We have a minute to discuss computing the correlation coefficient, which we will learn how to do, as I said, in some other programs. We'll learn how to do this in SPSS, and we'll actually get correlations in lots of in SPSS. The GSS Data Explorer can get correlation coefficients among GSS variables, and we'll do that in one of our labs, along with other tests that the Data Explorer, a part of the Explorer that we haven't used yet, can get these more advanced tests for us. But the basic process for computing the correlation coefficient is to just convert each variable to standard units, and then the average of the products gives the correlation coefficient. And so this is a nice way to think about it. You can do this in Excel very easily. If you want to get a correlation in Excel, I'm going to show you how, so you can do this when you are doing your homework for the next chapter. And we'll go ahead and use these data from earlier. Even though we do know there's already a perfect correlation here, you can see the data are entered. And in order to get the correlation, we're going to use a new feature in Excel. To do that, go to your Data tab. Under the Data tab, you can see that there's all these different options. And on the far right in my Excel here, you can see there's an area called Analysis. Analysis might not show up yet on your Excel. If it does, because this is an add-in that you need to activate, but it's very easy to do. So to activate this incredibly useful tool that you'll find very easy to use, simply go to the File area, go down to your Options, and then you'll see Add-ins on the left navigation area. At the bottom of the screen, you can manage Excel add-ins, so click Go. And you want to make sure that you have enabled this top add-in, the Analysis Tool Pack. You might be able to see it's already enabled in my Excel, but probably not in yours if you haven't used it before. And enabling the Analysis Tool Pack will make the Data Analysis tab show up, and that is the secret key to doing most of the statistical tests I think all of the statistical tests we're going to cover. So you'll find it pretty useful, and it's really intuitive to navigate. One small point of interest, sometimes even when you've activated this add-in, for whatever reason, Excel will deactivate it. So even if you've activated it, sometimes you might go in and say, where did my analysis tab go? If it disappeared, nothing to worry about. You simply go back to the file, down to your options, and reactivate the add-in. Okay? So now let's use this very useful add-in. I'm going to click Data Analysis, and you see that a window pops up here, and there's lots of tests listed. And in fact, we are going to learn most of these tests, many of them. Some of them we've already talked about. Random number generation. We talked about that for random sampling. This is how you could do that in Excel. We're not going to do that today. You get histograms. And today we're just going to get the correlation. So you can see that's the fourth one down. Correlation. I select the test I want. Okay. And then a new window pops up, and the same process happens for all of these analysis. For all of the tests you can do, you select the test, then you have to tell Excel where to find the data. So that's the input range, and I'm going to select both the variables, and I'm selecting the top row, which has the variable labels in it. Why? Because those you'll want variables labeled in later analyses, and it's a good practice to get in the habit of. So we selected our whole area with all the data. The data is grouped by columns by default, and that's generally how people group data when entering it in Excel anyway, so that you probably won't need to change. You want to check the box that says labels are in the first row, because then you're telling Excel this first row has labels. And then finally, just one other step, you need to tell Excel where to output the calculations. And you can put them in a new worksheet or just in a specific spot on the same worksheet, which is what I usually do. So I'm going to say, let's put the output here in cell D1. And you just click on the cell, you go back in, Excel automatically enters it for you. When we click OK, poof, here Excel has given us a correlation matrix. And you didn't have to do all these calculations. This would even work if we had multiple variables. Remember, we discussed there are scenarios where you have more than one predictor. You might have two predictors. When you've got two predictors, you just have another column in here. In between these, this would be our X2 column. This would be X1. And you follow the exact same procedure, this time instead highlighting all of them. No need to worry about that until later, but you'll see that this is very useful. And here Excel's given us our correlation. It's these ones in here. It's a little bit confusing because the correlation is 1 and the correlation of X with X is also 1. So to make this a little bit clearer about how that it's working right, I'm going to change a couple of these data points so we can see a non-perfect correlation in Excel. You might have noticed when I changed the data points, this output did not automatically update. It does not automatically update. If I want a new correlation for these new points that I've entered, then I need to run a new output or run a new analysis. I just go back to my analysis tab, click correlation, okay. Excel already remembers where the data is at. You can see it already knows where it was from the previous analysis, and it has saved all of my previous settings. So if I just want to overwrite this previous information, then I could just go ahead. Let's put it down below so that we can compare the two. So now you see that when I changed up these points, so it's not a perfect correlation, then this helps us guide us through the interpretation of this matrix that Excel spits out. This is called a correlation matrix. And the values that correspond to the variable and its correlation with itself, that'll always be 1. The correlation of X with X is 1. Correlation of Y with Y is 1. But the correlation of x and y, this is the one we're interested in, is 0.92. Ryan, you can't go outside. I'm sorry. Just relax. Please wait. Sorry. He made it pretty much the whole time, though. So you can see here, this is our correlation because it's x and y. Sometimes you see correlation matrices that are fully symmetrical, and it would be perfectly reasonable for a correlation matrix to look like I just created. So the correlation of x with y is the same as the correlation of x with y. It doesn't matter which side of the correlation matrix you look at. Do you see how that's symmetrical about the center? And just one final point to preview. Remember I promised we will be quickly moving into regression. So just a little preview on how Excel will calculate all these things for you. In the analysis tools, regression is also an option. I just went down there and selected it, and regression is where the calculations for the slope and the intercept are. So if you're thinking, well, this is great, we have the correlation, but you didn't tell me the slope or the intercept. That's because it's in the regression function. And regression and correlation are two peas in a pod. So to input a regression, we have to tell it which variable is x and y. So first we tell it y, our outcome, and then x, following the same basic process as before. I'm going to tell it there are labels, and let's put the output right here so we can look at that as well. And we're just look at this very briefly. Now it's giving us an error, but there's not actually any data there. You see, oh, I guess there was a little bit. You can see that there is, all of these things pop out. Don't be frightened by that. This is what happens when you do statistics in a statistical program of any sort. It's going to automatically pop out for you a variety of statistics that are commonly desired along with whatever test you're looking for. And so in regression, and you can see that the multiple R is just our regular correlation. You'll see later that this would be the correlation among several variables, but we just have two here. And so as long as you have two variables, R is the same, multiple R is the same as a regular R. You don't need to worry about these other ones yet. We'll discuss those as we get to them. We'll also discuss the meaning of the ANOVA part later on. So eventually you will know how to read all this. Don't be afraid when things pop up that you're not familiar with, though, right now. What you see down here at the bottom are the slope and intercept as promised. And here the intercept is giving us the coefficient for the intercept. It would be 0.66, and the slope x is telling us it says x because x is the label here on the predictor variable. So this is the slope for this variable x. It is a lot of information. Again, don't worry. You haven't learned how to read this other stuff yet, but it's going to pop it out anyways. It's going to give it to you whether you ask for it or not. Even if you just want this one piece, but that's fine. You just need to know where to find the data that you're looking for. And eventually this will all be legible to you, I can promise that. And so I thought you might find those procedures useful when you're going through your correlation homework, because I think it's much better for you to practice doing these calculations using Excel than doing them by hand, just because this is how people do it in the real world now. So to review, we got the correlation by using the correlation function, and it's right here at the x by y. When we get the regression, that'll give us information about the slope and the intercept. And it tells us the correlation as well in the multiple R category, which is, you can verify that's the same as your two variable correlation. We'll learn about these other terms on Thursday. And you scroll down to the final table that gives you lots of different predictions. Remember, we talked about how you'll predict using these same formulas, but to do them, you'll want to have your intercept and your slope. The intercept is listed first in the coefficients column, and right below it, the slope for the predictor variable. And Excel will put whatever label here you have as the label for the variable, because it thinks you know that this is the coefficient for X, the predictor. Remember, X is always a predictor, Y is, by convention, the outcome. Okay. Any other questions? Okay. Well, we will pick up correlation and regression again in our next lectures. And this is a set of topics that we will carry on through lots of our later work. So we'll keep looking at different variables and using these in chapters 8 through 10, in some of our later chapters, and also in our labs when we look at doing these procedures, but also we're going to look at how to model and test variables generally, and correlation and regression will be very important for thinking about that. So as you're going through these chapters, try to think about how you might apply these procedures to data that you might encounter in your work or in your academic life. You all probably have jobs where you encounter variables all the time. Start to think about, are these variables, how could I measure this? And then it'll help you gain more and more insight for making decisions about when to use correlation, regression, and the other tests that we have to look forward to. Have a great night, and remember, for the most efficient way, do some stats every day.